I was going to start or chapter unit 4, whatever it's called, today, but I think we need to just kind of review what we've done, and then we'll start 4 next week, because 4 is about the analysis of trusses, and that sounds scary, but really it's just all the stuff we've done except friction, thank God, in a major problem. So I want to make sure we understand where we've been so far. And the first thing is, okay, so we're up to date on assignments. By today, you should have all of the chapter 3. It's divided into 3 different chunks, but like assignments in, you should have 3.3 A, B, and C. You should have 3.9, right? And 3.7 A and B. And then the one that's on the calendar due today is 3.10 A through F, which is the moments. So is there any questions on any of those before I start my little talk? Did you get them all? You're still working on it, but you understand it, you think? Okay.
Yeah, I'm on D.
You're on D. Y'all understand the distributed loads and all that stuff? Okay. Well then, I'm just going to sort of run through where we've been so far, and then I have, so we don't necessarily have to depend on the book. I've made a review quiz, because we're scheduled to have a test once we get through with, or an exam once we get through with chapter 6. That's in like 2 more chapters. So I want to have a little quiz on 1 through 3 today, and make sure that y'all understand how to do the problems, and I'll hand that out to you after I go through this stuff. Okay? So, I lost my spot. Okay, so I'm going to sit down because I'm going to sort of type it on here. It's easier to type, I found, while I talk. You want me to turn on your screen? And then I can post it online for all those people that aren't here. But we're going to keep moving on, and that's their problem. Okay. So the characteristics of, hold on 1 second, tools, text. Okay, now it's not, there it goes. Characteristics of concentrated force. Concentrated force. Do y'all know what those are? There's 3 of them. When we have a force, what's one of the characteristics? You don't have to look it up. I mean, I don't want to take too much time, but do you remember? It's got to have some sort of power in it. What is that called? Magnitude. Force has magnitude. Magnitude. So what else does it have? Does it have to go in a certain direction? So it has direction. And the third quality of the force, or characteristic, it has a point of application. Right? Does that make sense to everybody? Those are the 3 things that are in forces. And that's what we demonstrate when we do our force diagrams. Like, if you have a force that's going like that, you know, it's going to have a magnitude of like whatever you assign it, 5 kips. First, It's going to have a direction. This one's going up and to the right, and it's going to have a point of application to whatever it's forcing. So if like it's a box, it's going to have the point of application right there. Make sense? You got to remember that. Okay. Then, so that's forces broken down. And let me see if I can show you a quick problem to help you. I don't want to give you one that I did. 1, 2. For instance, okay, I'm going to draw this little problem on here. We have a force going that way. That's 5 pounds. Or I'll just say 5 kips because that's easier to write on here. Then we have a point there, and then we have another force. This is a very simple problem. It has 2 kips. See, I can't write on this thing. So what's the resultant of that? Can't figure that out in your head. You need to go back to grade school. Are you looking at the screen? 7. Right. So the resultant is 7 kips to the left, right? So then if you get a little bit more complicated, I'm going to use this one. Let's say you have one that's going down, and then you have a force coming over like that. It's bad arrows, but then say this one is going to be 5 kips or pounds, and then this one is going to be 10. What would the resultant of that be? That goes that way. How would you figure that out? You could do it drawing wise, you know, with the lines, or you could do it algebraically. That's a 90-degree angle, right? But that doesn't necessarily mean that the force is going to be at 45, since one is greater than the other. But if you made that, made the 10 there, and the 5 there, if you were drawing it, that would be the resultant, correct? So that would be 5, and that would be 10. So how would you figure that resultant out? Right. So what is, if you have a calculator, so you got 5, well, we know that that's 25 plus 100, right? 25 plus 100 equals 125, and then we got to have the square root of that, is 11.180. And so your answer would be R. I'm going to give you some problems like this later. That's why I'm going over this. Equals 11.18, I think it said. And then you know and you'll draw a little arrow showing which way it goes. So that's that in a nutshell. And then they get more complicated, but you just got to remember, you know, your trigonometry, your SOHCAHTOA, your a squared plus b squared equals c squared, and you can pretty much, you know, if you rearrange these problems, figure them out. Is there any questions on that? Another thing that'll be on our little quiz in a little while, slide that up, is, and this is basically the same thing, but let me find that. Okay, say you have a force going that way. And that force is equal to 10 kips. So I would want you to find the dash line, the x and y of that force. So the x is always the horizontal, and the y is always the vertical. And I want to tell you that this is a 45 in this particular problem. So that's 45 degrees. Can't write on here. There. Okay. So how would you find the x and the y with algebra? Right.
Because sine equals to opposite over adjacent, and then you're going to use cosine, which is adjacent over hypotenuse.
Correct. So, in case my microphone didn't hear what you said, I'll repeat it. For the benefit of those that weren't here, you use the SOHCAHTOA, the law of sines and cosines. So your x, which is this thing, is going to be the sine of 45, right? Let's see. X over 10 equals the sine of 45, I think is how you do it. Let's try that. Or wait, I wrote it down earlier, I'm sorry. I got to look at it. So sine of 45 would give you
That would give you
your
your y.
y. Sine of 45? Opposite?
Yeah, because your angle is 45.
Oh, okay, yeah, you're right.
Your line would be on the other side.
Right.
So it would be opposite over hypotenuse, which would be y over 10k, and then you cross multiply, so it would be 10k times sine of 45 is equal to y.
Right. That is exactly right. So it's 10k times the sine of 45 equals y, and if we multiply that, where'd my calculator go? 45 sine times 10 equals 7.07 is the y, and you can pretty much assume that x is going to be the same thing because it's a 45-degree angle, right? But if you wanted to add it out, you would say cosine of 45, right?
Yeah.
Well, no, it's not the same.
You put a 5 instead of 45.
Oh, I did, okay. 45 cosine, there we go, okay, times 10 equals 7.07. So you're going to have the sine of 45, sorry for my writing, times 10 is going to give you y, and then cosine, right? Or did I get that backwards again? 40, 45. I feel like a first grader writing. Okay. Times 10 equals x. So that's how you do that. So that's, and you need to remember these formulas and get good at them because you're going to use them a lot in the truss analysis that we'll be starting next week. So then, after we did that, we went on to find the resultants of forces of more than two forces. So let me find one of those problems I can work with you. And I noticed I've gotten some information from a person that taught this in the past, and there's it seems like a simpler way to do this than, like, if you don't want to draw it out like we were doing in AutoCAD, like Bob doesn't seem to want to do that. So, if you have, let me just find one of these. There's that one. I want to make sure it's not one that I'm doing on the quiz. Okay. We'll see if this works together. Here's your horizontal line, or your line of horizontality, or whatever they call it. Okay, and then we have a force coming up from that line in that direction. Oops, why did I do that? Hold on. Stop. Going in that direction. That equals 10, whatever thing you have there. Then you got a force going in this direction. That one equals 16. You need that? There. Hold on. And then you have a force going down from that same point. That's equivalent to a 20 kip or pound force. Okay, and this, even though I drew this wrong, this is a 30-degree angle. Obviously more than 30. This is a 45. Looks like 95, but it's 45. And this one, the only information we have is that it goes over, or that we figured out, it goes over 4 and up 3. So the way that instead of drawing them all out, if you make a little chart, and this may, if y'all want to use this method, you can, or you can draw it all out. And you got X and you got Y coordinates. So your force labeled 10 over here, like that right there. Let me see. If you know that that's up 4 over 3, so if you figure out the hypotenuse of a 4, 3, then you could say 10 let's see, up 4 over 3. And we want to know the X. So X is to 10, right? Equals 4 after we figure out that hypotenuse. So what is that hypotenuse? 4 is 16 plus 9 is 25, so that's 5, right? Okay, that's easy. Because a squared plus b squared, 4 squared plus 3 squared equals 25, square root is 5. So 5x equals 40, right? Following me? So that means x equals 40 divided by 5 is 8. So over here in your little chart, you have 8. And you notice that it's going to the left, so it's going to be a minus, negative 8 for the 10x. For the 10y, you would just do it the other way. So you would say y over 10 equals 3 over 5. So y over 10 equals 3 over 5. So 5y equals 30. Y equals 6, correct? And that one will be going up, so it's positive. So we put that in our little chart there. then the next vector or array we want to figure out is number 16. So I'll line it up right there. So then we want to know the x and the y of 16, and we know that that's a 45. So the x would be the cosine of 45, right? Because it's adjacent over hypotenuse. So it'd be cosine 45 times 16. Is that right, Adolfo? Huh? Is that right? Are you following me, or are you doing something else?
I'm working on
Huh?
I'm working on 310.
Oh.
I'm stuck on 1 on 310.
Okay.
Because it's, yeah, it would be 6.
So cosine 45 times 16 would give you your x, and that would be 45 cosine. So that's just going to be, is that right? No, that's not right.
Where'd you get the 16 from?
That's the hypotenuse is.
Oh, okay, I see.
I didn't write it very clearly, but cosine, what did I do wrong? Cosine is opposite. It would be sine of 45, adjacent over
That
hypotenuse.
would be your y.
45 sine. That would be the, no, so katoa.
Sine is opposite over hypotenuse, and your opposite is going to be your x.
What's your adjacent? No, your adjacent is your x, right?
Yeah, I'm sorry, is your y. Sine is going to equal your y, cosine is going to equal your x.
Right. So, but, okay, 45 cosine times 16 equals
You put 6.
45
Put 6.
cosine time. Nice.
So divide that.
I'll get it one of these days. 45 cosine times 16 equals 11.31. So x, that was x, right? No, that was y? I can't remember.
Cosine,
Yeah,
that's your x.
x. So that was 11.31. And then your y is going to be sine cos, or 45.
45 is going to be the exact same thing.
Yeah, it's going to be the same.
You put 5 sine.
Ah! I'm switching between mouse and hand and drawing and times 16 equals 11.31, just to verify. So your x and your y are 11.31. Is any of those negative? Those are both positive, it looks like. So then the last one we got to figure out is this 20. So your x would be x would be adjacent over hypotenuse. So it would be cosine 30 times 20, correct? Okay, I'll use my calculator again. 30 cosine times 20 equals 17.32. So your x is 17, and that's going to be to the right, so that's positive. And then your y is going to be sine 30 sine times 20 equals 10. And that's going to be down, so that's a minus. So now you got this little chart without drawing anything. And then you add all these up. So that the x's are going to equal minus 8 plus 11.3 plus 17.3 is going to equal 20.6. And then the y's are going to be 6 plus 11.3 minus 10 is going to equal 7.3. Right there. And then to get your resultant, let me erase this. The resultant is going to be equal to the square root of the 20.6 squared plus 7.3 squared. So this is just a mathematical way to figure it out. So that's going to equal to, get your calculator, 20.6 times 20.6 equals 424.36. Can't draw very good. 424.36 plus 73 squared is 5329. Well, I did that first one wrong, didn't I? Damn it. Okay, let's see if I can try this again. It's 20.6 squared. Well, I was right. Plus, 7.3. That's what I did wrong. 7.3 squared equals 477.65. And if you take the square root of that, you're going to get 21.85 or 21.9. So if I'm going to erase that, so all that equals 21.9. So that's how you would figure that out mathematically, and it might be simpler for some of you than drawing it out. But anyway, the other thing we've covered besides friction, I'm not really going to get back into that because I think if we need it later, we'll do it some more. But right now we don't need it. Is the moments. Okay, moments. Anybody remember what a definition of a moment is? What's a moment? Anybody? What happens when something has a moment? What's it doing?
Moving.
Well, it's moving, but what kind of movement? It's not an emotional movement. A moment is a tendency to rotate. It's rotational movement created by a force. That's a moment. The magnitude of a moment is what? Magnitude of a moment is a product of distance times force. Remember that? It's pretty simple. Where the distance is measured perpendicular to the direction of the force. Perpendicular to the direction of the force. There is usually no point of application in a moment. Moments are added together algebraically. So an example for this would be you have a point A, or your the center of your rotation. You have a beam or a plank or something sticking out from that. You have a 2 kip force pointing up, and you have a 5 kip force pointing down at the end. And this thing is 4 feet long, and that 2 kips is right in the middle, so that's 2 feet on that side. So if you wanted to figure out the moment, which is usually spelled done with the M, equals 5K times 4 feet being the distance, 5K being the magnitude, equals 20, and then you call it kip feet. It's whatever your measurement is. And if it's going in this direction, clockwise, it's positive. So that's a positive moment. Then the other moment in this beam occurs, let me see, equals 2K times 2 feet equals 4 kip feet. That one, this moment here, is going to go that way, counterclockwise, so that one's negative. So you want to figure out the total moment of this is going to be, you just add or subtract those, it's going to be 16 kip feet. And then we do problems that get more complicated. Later on we talked about reactions. If you want it to be in equilibrium, all the moments have to be equal to 0, so you have to design your structure in that way. But moments, I think, are pretty simple once you break it down. The other thing you got to remember is if you have a beam with a concentrated load, or a distributed load. Well, that was wrong. Okay. That. You have a beam with a distributed load, and it says that this is just simple math, 10 pounds per foot. If it tells you 10 pounds per foot, that means you got to know how long that is, and let's just say that this is going to be 20 feet long. So 20 times 10 is going to be 200 pounds of total load. And since it's evenly distributed, that 200 pounds is going to be a point load right in the middle, or 10 feet from the end. So then you can figure out, once you have that point load, it's going to look more like this up here. And if you're trying to figure out a moment, over here, you can say 200 times 20 .
Wouldn't it be times 10?
Oh, you're right, sorry. The whole thing's 20. Now you're paying attention.
Yeah, because I gave up on trying to figure out the...
Okay. So 200 times 10 is going to be 2,000. And it's going in this direction, so it's going to be positive. So that's a distributed load of a moment. And finally, let's see if there's anything else I want to tell you about. I think we talked a little bit about couples. We didn't spend a lot of time on it, but a couple consists of 2 equal and opposite parallel forces. Let's write that out for you. And they gave you the example in the book, I think, like of a steering wheel. The moment of the shortest distance between them and the magnitude of one of them, or the product of the distance of force. That's what the moment equals in a couple. So, well, let me write that out for you too, because I'll put this on Canvas. So M in a couple equals the shortest distance between them, and magnitude of one of them, or the product of a distance of force. So in the example, we have another straight line. We'll turn straight. Yay. We have point A over here at the end. We have a force P coming down. We have a force P on this side going up. We have a point in the middle called O. And then we have a distance M and N. And a total distance of S. So what the formula is for this, see if I can get back in here. MA, moment about A, I'm going to say this, or I guess I'll do MA equals little m P around O, and MO equals NP around O. So the moment about A equals, there's supposed to be a space there. Oh well. The moment about A equals MP around O, and the moment about O equals NP around O. So those are equal. We didn't really spend too much time on that, but couples must be equal and parallel, oppositely divided, and in the same plane. Anyway, okay. I think that's about all. I've got a little, were you having trouble on one of your problems? Which one?
Yeah, on E.
10 what? What page is that?
It is on page 40. 51 is where the drawing is.
You're looking at E?
Yeah. It has two separate weights. Distributed weights, and I don't know how to figure out
Okay.
what we're supposed to multiply. I know that we should be multiplying. It's going to be 18R1 because the total length is 18. Is equal to. I know that there's a 3,000 times 14.
Mm-hmm.
But I don't know what to get
The distributed weights are like I said up here. You just got to break it down. The 6,000 pounds, they don't have per foot, so that's the whole weight of that whole distribution. So it would be 6,000 pounds right in the middle. So it would be 6,000 pound point load at the same place as that 3,000 pound. Does that make sense?
But would I do 6,000 times 14?
Uh,
Because it's 14 feet from the end.
six,
Because I did that. I did 14,000. I mean 14 times 6,000 plus 14 times 3,000 plus the 10,000 times 5, and I didn't even get close to the end.
no, what it would break down to is the way I did it was 14 R2 equals 4 times 9,000, because 3,000 plus 6,000 equals.
Which one
I'm looking at E.
you're doing R2? I'm trying to figure out R1.
Well, R1 is going to be 9,000. Well, if you figure out R2 first, then you just subtract it. But so I did it backwards, I guess.
Oh.
But R four I did R2 equals so I did that one first. You want me to write it out on here, or just talk about it?
Is it easier to figure out that one first? Is that
It seemed to me, I don't remember why I did that, but that's what I did.
so?
So if you have, because the sum of the moments equals 0, so 14R2 is equal to, let's see, I gotta retrace my steps. Yeah, because the two R's have to equal each other. So this is problem 10E in the book, right? So I did 14R2 equals 4 times 9,000, because that's the distributed load, plus the point load.
Where did you get? How do you get 9,000?
Okay, let me show you.
It's going to be the 10,000 plus the 6,000 divided in half.
No, if you look at your picture down here of your beam, you have a distributed load of 6,000 pounds. Hate that. Okay. Distributed load, 6,000 pounds. It goes for 8 feet, right?
Yes.
And it doesn't say 6,000 pounds per foot. It just says 6,000 pounds. So that's the total load. And since that's 8 feet and it's equally distributed, that's going to be right in the middle. So you can turn that into a point load of 6,000 pounds. And if you look at the drawing, there's already a point load in that same spot 4 feet from the end. That's 3,000.
Okay, so you're adding those
Yes.
on their own.
Yes. And then over here you got the other distributed load. Dang. Let's go up. That is 10,000 pounds. And that's evenly distributed. And that whole thing's 10 feet long, so that's going to be 5 feet from the end as a point load. Right? Because it's halfway. Right in the middle. Is that understandable?
So that's going to be.
And then you've got your other point load. Oh no, you don't have one. You just have your reaction, R2. If you go back up here, then back to mine. Insert tools, text. So I got 14R2 equals 4 times 9,000, which is this, that, plus 13 times 10,000. Get in there. Brought my parentheses. Technology sucks. Okay, sorry. Here we go. Let me write that over. Plus 13 times 10, 1, 2, 3. All that equals 36,000 plus 130,000, which equals 166,000. And then if it's 14R2, you can just divide that by 14, and then you get R2 equals 11,857.14. Follow that?
Yeah.
And then to figure out R1, you just have to say it's the reaction. So you've got your total load of 9,000 plus 10,000 going down minus your R2, which is 11,857.14, which equals 7142.86.
Yeah, I would have totally screwed myself up because that R2 is offset that 4 feet, so I would have messed that up on my own. Thinking that there was going to be a negative force going,
Yeah.
but technically they're all going the same way because it's spin on there, so then
Yeah.
makes sense.
Okay. So is there any other questions before I give you your little quiz? The quiz just counts as a quiz grade, but I want y'all to practice doing some other problems so that you'll be ready once we have a real exam. So I put the quiz, I scanned it and put it online, but I've got paper copies for y'all. And if you don't finish it before you leave, you can bring it next time. Okay? Stop this.